Okay, thank you very much everyone for joining today's physics colloquium. Today we have our great pleasure to host Professor Kenneth Burch from Boston College. Let me introduce him briefly. He's now the chair of the physics department at Boston College. And of course, probably many of you know, but he's a leader in optical spectroscopy in many kinds of quantum materials, including topological insulators, unconventional superconductors, and many kinds of 2D materials. I cannot raise all of his works, unfortunately, but recently what most stimulated me is the discovery of the Higgs boson. Probably he may have some time to mention that in his talk. Higgs boson in material at room temperature, which is very amazing result, and then has attracted much of attention. Today he is going to tell us about his recent research on another direction toward the sensing technology using quantum materials. So, Ken, please go ahead.
Thank you very much. Thanks for the nice invitation, and thanks everyone for coming. It's always great to be back in the city. I actually grew up about 8 blocks from here, so I'll do my best not to embarrass my parents. In any event, so actually today I want to tell you about something very different my group's been working on for, I don't know, maybe 6 or 7 years now. And also I hope this can be more like a discussion, so please interrupt if you have any questions as I go and if anything's unclear. So as you might know, sensors have become incredibly ubiquitous in our lives, as I'll talk about later. And in particular, whenever we do sensing, there's really a number of unavoidable trade-offs in the sensor that we're trying to make. And I'm going to try to convince you that, as Schrodinger told us, that we perhaps can use quantum to overcome some of those shortcomings. So, sorry, the jokes only get worse as the talk goes on. I'll warm you up for that. In any event, so I'll try to talk initially about what are some of those trade-offs and why we believe these so-called quantum materials might be useful. And just for, definition's sake, when I say a quantum material, what I have in mind is some material whose collective behavior has no classical analog, and that we can try to make use of that collective behavior in some sort of application. So I'll mostly focus on graphene and our development of what we call GEMS, the graphene electronic multiplexed sensor. So graphene is just a single sheet of carbon, and one of the kind of things that it became the most famous for is these Dirac electrons, so electrons that behave relativistically. And as I'll show you, these turn out to be incredibly useful for sensing. And there's kind of 2 properties of the graphene that go hand in hand. One is, as I'll show you, its structure makes it very easy to attach a wide variety of biological probes. And of course, it's biocompatible, being just just carbon. And the other is that these Dirac electrons give us a kind of natural marker of how much charge is sitting on the graphene. So we can electrically detect the presence of charge on the graphene and how much is there. And so what we rely on is we basically will attach a wide variety of probes that can then directly attach to the target we're interested in. When the target attaches, it then changes the charge in the graphene which we sense. And so we use that as a way of being able to detect a wide variety of different biological analytes, going everywhere from biomarkers in saliva to opioids, COVID and flu, and wastewater. And the device actually looks like this, just to show you. So we make these 1 centimeter square chips. Each chip has 20 devices on it, and we separate them into 4 wells, so each well has its own probe. So we can do multiplex sensing on the same chip at the same time within an hour. And as I'll show you, we even can achieve detection levels basically beating mass spectroscopy. So then if I have time at the end, I hope to tell you about some other work we've been doing in quantum materials. One is our interest in what's called nonlinear spectroscopy. So the basic idea here is that we shine light on a material and it intrinsically generates a photocurrent. And as I'll show you, that turns out to be related to the way the wave function evolves as it moves around the material, what's sometimes called the quantum geometry. But that also turns out to be very useful because you can make devices that intrinsically detect the polarization state of light, which you can hope to then use for various other optical sensors. And as I kind of quasi-promised Kota, I hope to talk about our work using Raman scattering. So my group also does a lot of Raman scattering So this is where you shine light on a material, every so often a photon will scatter, and kind of amazingly you can detect a huge array of different excitations. So it can be magnetic, charge, lattice, and using the polarization you can detect their symmetry. So doing that, we looked at a material which is a charge density wave and has an amplitude or Higgs mode. And interestingly, what we found using the selection rules, as I'll explain later if I have time, is that this mode is axial. It has a kind of handedness. And it was the first axial or handed amplitude mode of its kind, which we were really able to discover using Raman scatter. Okay, so I've now told you the whole talk, so if you go to sleep, I won't be insulted. As I said, the jokes only get worse. So why am I interested in sensing? It turns out sensing is kind of a huge field, right? So they're all over, we have sensors of many different kinds, whether it's, if you think about my phone, right? We have touch sensors, we have optical sensors, we're interested in sensing for communications, for biological applications, etc. And this has become a huge, huge field. And just to give you an example, so this is, Apple's latest iWatch. I promise they're not paying me to advertise. And in this watch, there's an enormous number of sensors. So there's two kinds of heart sensors, one optical, one electrical. There's a gyroscope, there's an accelerometer, there's 3 different microphones, there's of course the various kinds of radio antennas to do the communication, etc. Right? This is all in this tiny little watch. Right? So the problem is that this also adds to the cost and the complexity because each one of these needs its own material, its own device, its own operating procedure. Right? And so whenever you're thinking about sensing, it turns out that there's this huge kind of space that you're working in that you have to optimize. Right? So one is, of course, you want it to be simple, so it's easy to use and hopefully not too expensive to make. You want it to be specific, right? So you're detecting the thing you're interested in. So in my case, it's going to be I want to detect COVID and not flu. Or if you're thinking about a temperature sensor, that you're really measuring the temperature and not accidentally measuring the humidity as well, right? If you're also interested in achieving the lowest LOD, the limit of detection, right? How sensitive can you be? You also then ideally want something that does what we call multiplexing, right? That you can detect many things at once, right? So you don't have to have, like in the watch, a different kind of sensor for everything you're interested in. And finally, something that physicists often don't think about, but is really important is, of course, cost, right? If this thing is super expensive, no one's going to buy it or use it. So, this is sorry, yeah.
Sorry, what about linearity or dynamic range or the ability to?
Yeah, so that of course depends a little bit on the sensor, but yeah, indeed. You might also worry about, how much can you be sure that you know the concentration, for example, or over what range of concentrations can you operate. And in fact, I'm not going to talk about this, but if you ask me later, I can talk a little bit more about sort of in our sensor that's actually something we're now thinking about. But yeah, that's a great point. Yeah, so for example, this often comes up if you're doing epidemiology studies, right? Depending on the population you're sensing, you may be worried about, is there too much stuff in the liquid that's overwhelming your sensor? Or if you're doing an optical sensor, is it just going to get blinded by the intensity?
Or if I think of an alcohol sensor or a gas sensor, things that I want to know the value, not just whether it has.
Yeah, I guess your faculty meetings are more interesting than ours. I don't worry about alcohol sensors, but yes, no, 100%. So as I said, we have this complex, phase space that we're working in and we're trying to balance, but now, not only that I'm a professor, but I'm a chair, I'm very used to this complex balancing act. So hopefully I'll show you that quantum materials are useful for that. So just to take a brief sidestep, I just wanted to briefly talk about sort of what I have in mind with quantum materials and sort of a little bit introduction to my group since I haven't been here in, well, actually never for a colloquium. So as I said, I'm interested in these materials where you have this collective behavior that has no classical analog. So of course, in some sense, the most exciting one is entanglement. At Schrodinger, I think it was Schrodinger who taught us that, said that entanglement is kind of the fundamental part of quantum, right? So we're looking for materials that say have an intrinsic entanglement built into them, and I think this is still an ongoing challenge in the field, how to make that happen, how to detect it. Another is, of course, you can have the electrons in your material sort of collectively behave as if they're massless, right? That they have relativistic-like responses. In many materials that have collective phases, you can often get new kind of quasi-particles emerging. I will carefully use the word quasi-particle in case any high-energy folks are here. These are not, of course, real particles, but behave as if they are. And in fact, in my group, we've done a number of things in this regime. One, which I'm not going to have any time to talk about, is we've been working on topological superconductors, where we've been making devices to try to detect their emergent edge modes. And this is just one work where we did that. But in general, in these quantum materials, the recipe by which we make this happen is to try to combine different aspects of the material in some clever way to lead to this new behavior, which we then want to make use of. Right? It can also be the utility of it, right? That you can have, say, the charge and the magnetism closely tied together, et cetera. But it also is why it's quite challenging, right? Because we have to disentangle what are the key components of the material that are leading to the behavior that we're trying to observe, let alone trying to control. So in my group, our approach, we call ourselves LASE, the Laboratory for Assembly and Spectroscopy of Emergence. And our approach is based on one that's, I think, worked out well in my own life. We try to combine distinct materials to generate new phases of matter that we detect via their topologically non-trivial excitations. Oh, good. Okay, so how do we do that? So we have two components of the lab. One is the assembly and one is the spectroscopy. So we've built what we call a clean room and a glove box. So this is something like 25 feet long. It's on the right-hand side, we have all the characterization, not all, but we have characterization facilities, so we can do Raman, searching for flakes, we have AFM, etc. On the left-hand side, we have a spin coder, mass lithography, and 2 deposition tools, so we can do etching or deposition. We can do all the lithography inside this inert atmosphere. So for students in the room, if you're sick of the bunny suit, come visit my lab. You can do fab without bunny suits. And we think of this actually as a user facility. So if you're interested in working on something that's air sensitive, please come and visit us. So we've collaborated with many different groups on lots of different things, including even actually a battery group who we worked with to image the battery as we were running. We also, on the back, have a vacuum suitcase. So you can either bring a material in from a vacuum sensitive system like Javad's, I don't know how many MBEs he has now, but anyway. Or you can take it from the glove box into our low temperature Raman setup. So we can actually go and do our optics without ever seeing air. And that's been incredibly useful. We like Raman, as I mentioned earlier, because we can measure a huge variety of different properties of these emergent materials. We also do conductance measurements, basically sort of, you can think of them like tunneling measurements. We do this at low temperature and high magnetic field. There we're often looking at superconductors and their emergent modes. And finally, we also do nonlinear spectroscopy in my group, so basically shining a laser on a sample and measuring the resulting photocurrent. And if I have time, I'll get to this last thing in the Raman later. Okay, so that's just a kind of quick overview of the group and the things we're doing, and there we go. All right, so now I want to sort of switch gears and just really focus in on this this aspect where we've been trying to generate this new kind of biosensor, which we call GEMS. So I want to talk specifically about the kind of sensing that we were interested in, which is often called point of need sensing. So you're probably all used to the idea, you know, you cough or you're sick or something, and you have to go to the doctor to get a test to tell you what's going on, right? And actually in many health areas, that's the case. And also in epidemiology, it's a similar problem, right? That you're often sensing for a whole community rather than the region that you're interested in. So there's kind of two aspects of this, right? There's the personal healthcare, how can we detect what's going on in your own body and so on. And then the other is the kind of collective, you know, how can we look at health problems as they emerge at the length scales, if you will, that they're relevant. So the tools that we have in our toolkit, there are actually quite a few, and I'm not going to go over all of them, but just to give you sort of the extremes. On one end is so-called PCR. So depending on how complex you want it, you can spend as much money as you want. But this is one of the most expensive examples, the BioFire. It can detect 21 different analytes with incredible sensitivity. And essentially what they do is you split up the material you're interested in into its fundamental DNA. You then have a process by which you copy the DNA many, many times. And then you have a probe which is selected to only attach to a certain sequence of the DNA, which you detect optically. So this can be remarkably sensitive. You can get down to very, very low levels, but as you can imagine, requires a lab and is not cheap, right? On the very other end of the scale is the personal test you've probably all taken many times, which is working off of a lateral flow immunoassays, where you basically have a probe You flow over, over this piece of paper, essentially. The probe will hopefully attach to the thing you're interested in and then attach to an antibody or a test line. And then there's the control line. You've all, I'm sure, used these, right? So these are great because they're super cheap. They're not so great because multiplexing is practically impossible. And also, of course, their limits of detection are way too high to be useful in most cases. Okay, so we wanted to see if we could sort of find a way in between. Could we find a way to make something where we could sense lots of different things, maybe not quite with the sensitivity of PCR, but still sensitive enough to be useful, but also cheap enough to be useful. Okay, so, excuse me, one other thing I need to apologize for now is, unfortunately in this field, there's like, I don't know, there's more different units for how to do sensing than there is in magnetism. So I'm going to try to stick to these so-called picograms per ml. So just to give you a flavor, and I'll show you this again later, the rapid tests are up at the levels of 200 picograms per ml. Lab-based tests tend to be 5 picograms per ml or better, and that's really actually mostly mass spec. PCR can do it better than that. So many groups have been trying to find a way to do this with electronic devices. And the approach that's typically taken is to use a semiconducting gate. Okay, so you have some semiconducting channel, you have a capacitor and a back gate, which is just your metal to try to change the charge. You measure your source and drain, and this is of course a capacitor, so you can have some region where if you plot the, say, source drain current versus the gate voltage, you'll see it turn on, right? So that would be, for example, this region here. And so what you're doing, of course, is just changing the charge in the channel, right? So the idea is if you can then chemically attach to that some probe, where the probe is selective, so often what's used is what's called an aptamer, a DNA sequence that only folds on the target you're interested in, right? Then when you expose it to the target, right, if the target has the wrong stuff, it just bounces off the surface. And if it has the right stuff, say COVID, then ideally this aptamer will just grab that target for you. And one thing that took me a while to get used to is in biology, things are almost never neutral, and so that target is charged, and so it will act like a capacitor to kind of gate your semiconducting layer. So then what you would do is to try to see a change, right, in the conductance of your semiconductor. So unfortunately though, when you do all of this, you typically have to operate in liquid, and it turns out that liquid will have ions in it, and so as a result, you'll get a lot of screening of the charge just at that surface. Okay, and so actually what happens is if you have this kind of so-called double layer, you basically form a capacitor at the surface, and that will dramatically reduce the signal you get. So basically your relationship between the current and voltage is of course affected by how much charge you can induce, and that is dramatically reduced by the fact that you have this huge double capacitance layer. So another problem in this field has been that to do this, you're often trying to chemically attach your probe to your semiconductor. So you just naturally are going to disorder it. And in addition, you're going to need some dielectric layer because, as you can imagine, silicon doesn't react so well to these chemicals, and so you're going to have to add something to protect it. When you do that, you're now moving the charge further away, and you're adding noise from your crappy oxide layer at the surface. Right? So as a result, these kind of detectors have essentially not found mass applications because they have all these various limitations. So a number of groups, including my own, have been trying to use a very different, maybe not very different, but a different approach using graphene. And graphene has a number of advantages to it. So just to remind you, this is a single layer of graphite. It's basically, you know, this carbon honeycomb layer. And it turns out there's a molecule called P-base. And this P-base has these 4 benzene rings and can just pi stack directly on the graphene. So it just sits there without disordering it or charging it. It's just sort of bound to it. And nicely, it has this tail, and onto this tail, we can attach a wide variety of different probes. So basically, we can very easily, just by, you know, essentially just exposing the graphene to this P-base along with the probe we want, attach a huge array of different probes without having to reinvent the chemistry every time. Okay? So the point is that graphene has a lot of advantages. You have this biocompatible material, the attachment is super easy, and it turns out if you prepare it properly, it's totally insensitive to pH. Another advantage, though, are these relativistic electrons I was telling you about earlier. So the reason these are useful is because you have this low density of states at the Dirac point, graphene tends to have very low noise, right? So there's just not a lot of places for fluctuations. It turns out also that it has what's called a quantum capacitance. Basically, the capacitance of the graphene, the intrinsic capacitance, is enormous. And so it almost balances out this double layer that you would face at the surface. And finally, you have what I call an electronic marker. So the point is that remember that the conductance is going to depend on the filling, right, the number of states at the Fermi level. And so when the Fermi level is right there at the middle, right, the resistance will hit a peak. So by measuring the resistance versus some gate voltage, I can tell exactly how much charge is sitting on my graphene. So just to show that a little bit more specifically, so what I'm doing here is applying a liquid gate voltage, right? So I'm just tuning the charge on the graphene. And when I hit the right voltage, it's when I move that Fermi level to that Dirac point. So by measuring the voltage at which the Dirac point shows up, I know exactly how much charge is on my graphene, and therefore how much concentration has attached. Okay? And so what we're going to do is to basically make our devices as clean as we can, and look to see where this Dirac point goes as we expose the target. And then we'll have to calibrate, as I'll show you in a minute, how much voltage corresponds to what concentration.
What about the current that flows directly through water?
So the water is orders of magnitude more resistive than the graphene. So we basically see no current from the water itself. I'll also show you in a minute that we actually protect the device. We protect the device from the liquid. So if I don't answer your question, feel free to ping me again, but I'll show you in a second. That's actually crucial to the device. Okay, so you might have be wondering at this point, this all sounds very nice, but isn't graphene that thing you make with Scotch tape, and how are you ever going to scale that up? That's a fair question, except nowadays you can actually buy this graphene on huge wafer scales from multiple companies. So it's actually becoming a kind of almost commercially viable product.
Are you doing like lock-in between the source and the drain?
Nope, we just do DC measurements.
So there's no leakage current from like the silver chloride through the...
We don't actually. So we no longer use silver chloride. We actually use platinum gates, and there is probably some leakage current, but it's so low that we don't notice it. Because again, remember my graphene's at the order of a kiloohm, so we don't need much current. I mean, what I'm saying is that resistance is tiny compared to the resistance from the gate. Going back to the question that was asked earlier. Okay, good. So what do the devices actually look like? So we prepare our substrates like this. We have a source and a drain that we will then put the graphene on top of. I'll show you that in a minute. And on the same chip, we actually put the gate as well. We then have an aluminum oxide layer, which we use to protect or passivate the device from anything it's going to get exposed to. And we just open this little window. So what's really going on is underneath that window, there's actually a sheet of graphene that we've cut into the right shape, and then we've passivated the whole thing with just this aluminum oxide, except for that little window where our sensing is going to happen. Okay. So we choose that window, of course, to try to optimize our signal levels. There is a slight annoying part of graphene, which is it turns out the surface is hydrophobic, which, as you can imagine, is a problem because the water is going to go around it. So, and it's especially worse because the side is actually hydrophilic. Because graphene likes to torture me, I guess. So anyway, this is where this passivation layer becomes really crucial, that we have to make sure that the water can never see the edges, otherwise it'll just go underneath, which I say from experience. In any event, going back to the question I was asked earlier about going through the liquid, so another problem is that you're trying to gate right through this liquid, and ideally you hope that your gate is just completely affecting your graphene, right? You're moving ions to the graphene channel. It turns out, though, of course, if you don't passivate the rest of the device, you'll gate in other places. And so that turns out to be a huge issue for us, so we have to be very careful about passivating everywhere but the active region. And so the way we do, and of course, we also want to make sure that there's no contaminants sitting on the surface from the fabrication, et cetera. So after many years now, we've actually optimized the process. What we do is we get our graphene from a company that's then transferred it onto our device. We then bake it overnight. That tends to get rid of all of the extra, there we go, all of the extra resist. It also gets rid of any trapped water. And then we cool it down, and once it's done cooling down, we apply a very thin passivation layer to the surface, which allows us to do all the fabrication without ever getting the graphene dirty. So we have some tricks that I'm not going to bore you with where we can then open this up at the last minute and keep the graphene pristine. And we know this after many years because we see things like this. So for example, if the passivation is not working well, you'll notice there's actually kind of two humps in this resistance versus gate voltage. That's because in some place it's leaking somewhere it's not supposed to go. So when we make our devices correctly, this is what they look like. Of course, when I say we, I mean my students, but nonetheless. So we've now really optimized the fabrication, which turned out to be quite crucial to get the sensitivity that we want. Okay, and just when we're all done, as I showed you earlier, this is what it looks like. So we make a centimeter square chip. We have 20 devices on the chip. We separate them into 4 wells, and when we're done, it looks like a penny. And just an interesting side note for the students, if you ever submit to ACS Nano, they'll make you take the penny out, very annoyingly. But the other nice thing about graphene is we can, as I mentioned, use a wide variety of probes. So in principle, we can use antibodies or aptamers or peptides. Unfortunately, the Debye screening length of the liquid is quite short, so we end up having to be stuck with either peptides or aptamers. And that has worked well, but nonetheless is a limitation. We can't use antibodies. Okay, any questions about that? Sorry, Philip.
Just a quick question, can you gate from the back also? You have a gate on the back?
You can, but it's super inefficient. So what's beautiful about gating through the liquid is with like 1 volt, it's roughly the equivalent of about 100 volts from the back gate.
I see, that's
And
the
if you
kind
think
of
about a real world device, you want to operate at 1 volt, right? So this is what's beautiful about this liquid gating.
Thank you.
Yeah.
Sorry, what's an aptamer?
Oh, thank you. Yes, good question. So basically an aptamer is a DNA sequence that's been, for lack of a better word, evolved so that it only folds or unfolds around a specific target. So for example, roughly speaking, the way they make them is they start with like a huge pool of DNA sequences, they expose them to the target, and then they basically have a process by which you eliminate the ones that don't stick to the target, and then you also make sure they don't stick to things you don't want. So for example, opioids when you're trying to measure COVID. Yeah.
Does that mean that once you go through that process with the aptamer, then you can just sequence it and then just replicate the
Correct.
sequence that...
In fact, in my group, what we do is we tend to find a paper where they've, if we trust them, have done a good job with the aptamer, and we just order it from a company. It's kind of amazing, actually. Yeah. And part of why we do that is because we don't know anything about biology, so. All right, by the way, just to show you, this is not, we're trying to actually make this viable. So we are now focusing on doing whole wafer scale. So this is a 2-inch wafer where we make 44 chips in parallel, which is almost working this way. So it works most of the time, but not enough. And we are also trying to make it easy to use. So this is actually an undergraduate in my lab developed this. So it's a handheld device. So what's beautiful is because all the voltages are small, the resistances are reasonable, you can use very cheap electronics. This whole thing, I think even with the chip, costs about $50. So, and anyway, actually for me it costs nothing. I just asked this. All right. So one of the first things that we wanted to work on was the topic of infections, and part of at the time what we were thinking about was actually the problem of antibiotic resistance. So as you may know, like when you have a cold or something, you call the doctor, and then the doctor doesn't really know if it's a bacteria or the flu or virus, etc. They just basically prescribe you antibiotics and kick you out the door. And part of that is because there's not a good test that would rapidly tell them. So for example, the rapid test that we all had to take for COVID, might tell you it's not COVID, but wouldn't tell you what it is, right? Another problem is often the limits of detection were so high that it's kind of useless. So people have tried to do multiplexing with these rapid tests. I don't know if you can tell the difference between which strip is the one that tested positive and which one wasn't, but I certainly can't, right? People have tried this with graphene before us, and they would do a slightly different approach than us. So they would just measure the current, and then as soon as they see a jump in the current, they would call that a detection. In any event, they claimed they could get to 1 femtogram per ml, which was impressive, except that was in water. When they tried to measure in actual serum, they lost 4 orders of magnitude in their sensitivity. And as far as I know, they've never reproduced this data. There have been other groups that have used graphene trying to sense various aspects like the antibodies and so on, but their limits of detection were incredibly high. They were 250 nanograms per ml. so sort of too high to actually be useful. So with that in mind, we had actually originally done some work where we showed that we could measure in saliva a biomarker. So I'm not going to go through the details here, but basically just to give you an idea. So here I'm showing you the shift of the Dirac point versus the concentration on a log scale. The blue is the data, and the red is where we tried a control experiment, just to make sure that we don't get sensing when we don't want it. And this purple curve is what's called the Hill equation. So this Hill equation is basically accounting for this, how often are you grabbing or letting go of the target? And so it's actually a way of checking that your device is behaving the way you expect. In any event, so inspired by the fact that we could measure in saliva, we thought, can we look at bacteria? And we were thinking about this antibiotic resistance problem. So this is actually quite old now, this data, but it turns out there was a study about a decade ago that showed that something like 40 million antibiotics are prescribed in the US per year, of which 27 million are completely unnecessary. And so this is really driving this problem of antibiotic resistance. And so we were hoping that we could make a detector that would make it simple to tell whether you had an infection with bacteria or not. So this was kind of our earliest work. We looked at two different kinds of bacteria. And we had these peptides that were kind of neat in that we could get two different peptides that were otherwise the same, except one would actually attach to the bacteria we're interested in, and one would attach to nothing. So we would expose the device to a specific bacteria that was meant for the probe, so in this case S. aureus, and we would get a large Dirac voltage shift, and when we try it with a control, we'd see nothing, so that was good. We would then check, of course, with other bacteria to make sure that we don't get any false positives, and our signal levels were fairly low, so far we were very happy. We then checked what if we tried a different bacteria where we had a different probe, and this is all again on this same chip. And again, we could get very large signals with the probe and very low signals with the control. So far everything looked great. And this is when I learned that as a physicist, once in a while you should be humble. Not often, just once in a while. And the reason is the following. So my postdoc brought me this data, and he showed me this picture, and it turns out that little black dot that you see on the device, that's a single bacteria. So I was like, this is amazing. We can detect a single bacteria. I was super happy. And we ran and told our bio colleagues, and our colleagues said, well, what was the concentration of bacteria in the liquid you needed to get the one on your device? And so we told them, 10 to the 7 cells per ml. And for those of you who don't know, your patient is far beyond dead at that point. So I was a little depressed. But then I remembered, actually in fairness, my postdoc remembered, this work by another group where they used graphene to do something called dielectric phoresis. So this is where you apply an AC field, and if you do it right, you can actually push the bacteria to your device. So these little bright dots you see are actually bacteria that were attached to the graphene using this AC field. So we thought AC is too hard. Let's try something simpler. So we just applied a pulse on our gate that was of the wrong sign to just push the bacteria to the device. And this worked remarkably well. So we were actually able to push the bacteria straight to the graphene. And as a result, we could reduce the limit of detection by 3 orders of magnitude. So we were actually able to get down, at least with S. aureus, to clinically relevant levels, at which point we were quite happy. Unfortunately, though, it turns out that the personal home healthcare space is incredibly flooded. And so we, after this work, decided to leave it for various reasons and have switched to a slightly different topic, which is what's called wastewater-based epidemiology.
Just one question about that.
Yes,
How long
please.
does it take to get the result?
5 minutes. In that case, that's when we use the electrophoresis. Sorry.
For the at-home devices, how long do they last? And do you have to wash them in between? Is there
Yeah,
some
so
sort
we never got to that point.
Okay.
Yeah. That's a great question. So we're just now starting to worry about that.
Okay, but they can be reused. It's not a.
We actually, the problem there is whether the probe can let go. So in the case of the peptides, we didn't know how to get the probe to let go. In the case of the aptamers, what I'm told is it should be possible, but we haven't tried it. So. Yeah. But that's, if the chip is not so expensive and you just have to change the chip but not the electronics, under the right circumstances, who cares? You know what I mean? Okay, great. So, so you may have heard about wastewater-based epidemiology. At least before COVID, I had only started to hear about it. It turns out that we all ingest many things. It can be, I'm sure no one in this room, but drugs. Can be a toxin, can be a bacteria, right? And then you metabolize it, and let's say you donate it to the wastewater system. Okay. So it then makes its way down the sewers to eventually a wastewater treatment facility where someone can go and collect the wastewater. They can then ship it to a lab, and then someone, some lucky grad student in the lab has to handle this wastewater and put it through some sort of testing system to then measure whatever the target is that you're interested in. Okay, and then finally that information can be sent to your local health official, right? So in some sense this is kind of amazing. We can now track COVID, flu, et cetera through the wastewater very accurately. But of course you tend to track, say, the whole city at once, right? Because you're just looking at the wastewater facility, and part of the reason you do that is you need a lab, right? And the reason is you either need to use PCR if you're interested in something like a bacteria, a virus, et cetera, or if you wanted to look at something like drugs or other toxins, you need mass spectroscopy. So this is already a problem, right? You need two very different kinds of instruments and experts to run them, and chemicals and lab space, et cetera, right? And so this has really limited the widespread availability of wastewater-based epidemiology. And in fact, something like 65% of wastewater epidemiology is done in high-income settings. Okay, so we were thinking, well, what if we could get GEMS to work in wastewater, right? Then you could actually use it, if you want, street by street or dorm by dorm, et cetera, right? So that you could do early detection of viruses or other infections. Or you could do things like, how do I know whether my intervention for, say, opioids is actually working? I don't want to go and test everyone in a population. This is a way of testing kind of locally to see if it's actually doing the trick. There's also lots of other potential applications, for example, looking at disease outbreaks in farms, et cetera. So at this point, you might be wondering, wait a minute, didn't he tell me he likes to work with quantum materials? What does that have to do with poop? But I sort of feel like the connection is obvious, but maybe you don't agree. Okay, tough crowd. Anyway, all right, so what did we do? So our first work was actually looking at opioids. Again, with this idea that you could try to use this as an intervention technique. So what we did is we had 4 different probes, one in each well. So in one well, we were testing for neuroxycodone. In another, we were testing for EDDP, or basically the metabolite of methadone. We then tested also for norephenol, again, a metabolite of fentanyl. And finally, we had a 4th one, which is just a control well to make sure everything's going okay. And so this is what the data look like. So first we tested in PBS, just basically salt water. And we do it as a function of concentration, and we start with the NX well, and we put in an enormous amount of the other things to make sure we don't detect them, right? So in this case, the EDDP, and then the blue dots is when we go back and we put increasing concentrations of the target. Okay, and it follows beautifully this Hill equation. We can extract out the limit of detection, which in that case was 4 picograms per ml. So we were quite happy. Except then we tried it in wastewater, and we lost about an order of magnitude in the detection. Still good, but not great, but that's fine. So then we said, okay, what about the other wells? So in the other wells, we get similar results, and we found that we could actually detect roughly at the same limit of detection in all 3 cases in the wastewater itself. And then this goes back to, I think, your question about the linearity. So it's roughly linear in concentration over some range. There is a point at which we saturate, but in our experience, that point is so high that it's irrelevant.
And so are the people.
I'm sorry?
And so are the people producing the wastewater.
Yeah, actually,
High joke.
yes. Well, I'll come back to that in a minute, but good point. In any event, so we are still, in this work, we were still about an order of magnitude worse than mass spectroscopy. But nonetheless, if we thought that we were doing pretty well. And in fact, we were better than sort of optical-based techniques that we were competing with. But still, like a good PI, I'm never satisfied. So we went back to the drawing board and wanted to see if we could do better. So we then made a number of improvements to the device. Some of them were actually changing the way in which we prepare the molecules when we attach them. Some was improving the design and also the passivation. And then we decided to do something maybe a little more relevant. So we put flu in one RSV in another, COVID in the third, and then finally we put caffeine. And the reason is when you do this wastewater-based epidemiology, getting actually to your excellent joke, you don't know how many people are donating the sample, right? So how do you normalize the signal, right? How do you know whether it's one person who is highly infected or 10 people with very low infection levels, right? So the idea is that can you add things to normalize? Caffeine works well, at least on campuses, which is where I work, but there are other options. I'm gonna skip the details, but to make a long story short, we've managed to improve our detection limits now by orders of magnitude. So we're at the order of about 100 femtogram per ml for each one of the targets that we looked at, and that's actually 2 orders of magnitude better than mass spectroscopy. So we think that we've now achieved a level that could actually really be relevant for doing this wastewater-based epidemiology, sort of, at the very local level. And we're just about to start a series of experiments using actually wastewater BC and going apples to apples with PCR. So coming soon. Anyway, I'm going to stop for a moment, see if there are any questions, because I'm going to switch gears in a second. And I'm thirsty.
How do you functionalize the different regions?
Excellent question. So remember I said there's this P-base molecule? So what we do is we actually pre-attach the probe to the P-base, and then in each well we put down the probe just for the thing we're interested in. Right? So in one well you'll have the COVID probe, in another well you could have the bacteria probe, whatever you wish. Yeah. So another thing we're actually very interested in is how many different things can we do at once, right? So right now we're doing 4, but you'll notice that I've already shown you that we can measure everything down from caffeine proteins all the way up to a whole bacteria cell, right? So that's also kind of unique. And it's really just because the device is probe agnostic, which is a little weird just for someone who works at a Jesuit institution to talk about. But anyway.
Caffeine is misspelled.
I was just making sure you're paying attention. Thank you.
How long does this device survive once you get it wet?
Oh, great question. So actually, another experiment we're just about to start is not exactly what you asked, but similar, which is once you attach the probe, how long does it last? And we haven't done that. So what we do now is we attach the probe, we let it sit for 45 minutes, we wash off, and then we start our experiments. But the experiments will take all day when we do the full concentration.
But so like right now somebody has to like pipette the toilet in and then you do it once. Like, is there a future in which this is like installed in my toilet and it just tells me when I'm sick?
That's the idea. Maybe not your toilet, but sort of the collection point in your building. So just to give an example, that sounds a little crazy, but actually UCSD during COVID, what they did was they actually didn't lock down at one point. I mean, they did it first and then they switched to a model where they had, I think it was 300 different samplers, but then some poor grad student or postdoc had to go and collect every day, bring it back to the lab. Of course, it was automated in the lab. And then what they would do is you would go to work, and if there was a detection in your building, they would tell you, and then so people had to go get tested individually. So that is nice, except that it's super expensive. So the idea is this could be the replacement for that, right? So you can imagine in K through 12 schools, what if we knew immediately if there's some outbreak at each school?
But you
That's
already
kind of
do.
the idea.
Those kids are germy.
What? Well, I'm not going to say anything about NYU students, but okay.
K through 12.
But that's kind of the dream that we have. And so that's why we're going to start doing this. Yeah, so one of the things we need to do is incorporate fluidics with the idea of, not really microfluidics, but just fluidics. And we also have some ideas about how maybe robotically to do the attachment, so you could really scale it up. I mean, to be honest, I'm a physicist, right? So I was at first happy with proof of principle, but I'm not so happy, so we're now trying to get it out of the lab into reality.
And when you chose the virus, you chose it just because it's a common virus, not because there is something that makes it easy to detect.
Correct, yes, indeed. We actually were thinking about respiratory viruses in particular.
And
That's right.
meningitis, that would be useful.
Yeah, meningitis is, the only question is whether it can be detected in wastewater, but other than that, yes. Yeah, so actually, we also were thinking about E. coli, cholera was another one, so, yeah. But basically, if you can give me a probe that works, so far our experience is we can make the device work.
How much does these cost?
Well, the first one is free.
Right.
No, it's a good question. So we actually had to do a back of the envelope estimate, and if we do it in my own lab, which is not the cheapest solution, it's like $30 per chip. So it's not free, but it's not bad, I would say.
Could you use this for ecology or wildlife protection or something like that, sampling water in lakes, for instance?
That's a very interesting idea. So the short answer is I'm not sure, but we have thought about something similar, which is looking at heavy metals. So it turns out that you can get aptamers that are claimed anyway to work for a specific heavy metal. And we've also thought about could you use it for pollutants in just regular water streams. And in fact, when I gave the farm example, that is one of the things we were thinking about, is actually farms have a lot of water waste that goes mostly unregulated. Yeah, in fact, I was gonna say this later, but maybe I'll just say it now for anyone in the audience. I actually wasn't totally kidding about the first one is free. Like, we are happy to work with people to see if we can, find other uses for the device.
Yeah, and so right now it's based in water, right? Because like you would put this in some sort of liquid.
So we have done it with saliva. Saliva is a little annoying because it gets a little bit gelatinous, so we had to dilute it. And in fact, what I didn't tell you is for the wastewater, we actually do filter it and then dilute it a bit. The reason that's actually one of the problems for the limit of detection, but we have to do that because otherwise the what is this called? The pH level is too variable. So if we just dilute it, that seems to fix that problem. But anyway, I'm sorry, yes.
And so I was just wondering, since Professor Caban brought up the ecology portion of it, would there be a way that this could just work in air?
And that's a good question. So there are others who are trying to do what they call an electronic nose. I think we're probably, if I'm honest, I don't think we're sensitive enough. I think, and in my experience, you can actually get much better sensitivity, but you sacrifice the specificity. Okay. Maybe just in the last few minutes, let me tell you about some other work that we are doing, or as I like to say, the other things I learned in the mean streets of New York. Okay, so just in terms of GEMS, some of our next steps. So we've been thinking about a little bit, could we incorporate this with other sensors? So far we've made the devices on silicon, but we could not easily, but straightforwardly make them on transparent substrates. So if you have your favorite optical technique you'd like to incorporate, or for example, maybe doing it with NB centers or quantum sensors, we're very interested in that. Also, I really am not a biophysicist, but happy to share the devices. So if there's some way that this could be interesting, we've thought about making use of them, say with the electrophoresis combined with fluorescence, etc. And then also one thing that is maybe a little bit closer to my experience, we've been thinking a little bit about, is this a nice way to incorporate some of the organics with quantum materials? So for example, in molecules, it's very straightforward to get things that are chiral and handed and so on, and could this be a kind of pathway to that? And then lastly, one thing I didn't talk about is I gave you this nice little story about, charge transferring from the target into the graphene. I am being recorded, but anyway, I think that's wrong. So this is kind of the lore in the community, but you can very quickly tell why that can't be true. So remember I showed you here that you can have this bacteria sitting on your device, and I could detect a single bacteria because my whole Dirac point would shift, but it doesn't make any sense. The Debye length is 1 nanometer, and this device is something like 20 microns by 10 microns. So the only way that could really be true is if what the bacteria is doing is changing the surface capacitance. And so it's really like what you're doing is not changing the doping, but changing the capacitance. And so one thing we'd like to do is try to go back and better understand the mechanism of how it actually works, rather than just the lore. So with that, I'll just skip ahead. There we go, okay. So as I mentioned, one other thing that we're interested in are, can you use some of these quantum materials for optical sensors? So just to briefly remind you about how most optical sensors work, a lot of them work as basically diodes. You have some PN junction, you send your light in, you excite the electron to your conduction band, and then the electron basically falls down and you collect your current. Okay, so these are kind of what's in most, I would say, optical sensors that you would use. On the other end of the scale is basically photothermal detectors. This is what's mostly used in the infrared. You know, you basically heat some region of your material, you generate a voltage through the Seebeck effect, or you change the resistance, and that's what you detect. However, while these are very mature technologies, can be very sensitive, they tell you nothing about polarization of the light. Right? So if you want to learn about polarization, you had to add polarizers and so on and so forth. Why would you care about that? Well, for example, if you're interested in low light imaging, right? Here's an image taken of some bolts on a table in low light imaging. But instead, if you measure the polarization dependence of the response, you can actually do much better than you would with just a standard intensity. And of course, this is true for communications or if you're thinking about quantum optics, etc. So this is a place where nonlinear spectroscopy can be very fruitful. The reason is that in nonlinear responses, you're looking at things, say, at second or third order, where you respond to, say, the second or 2 or 3 electric fields. You have an expert sitting right here, so if you have questions, ask him later. But hopefully what you can see is that this could be very sensitive to symmetry, right? So the kind of currents that I get will depend a lot on whether I use, say, linear polarization or circular polarization, etc. So it also turns out that this is very sensitive to what's called the quantum geometry. So one measure of quantum geometry, which is really how does the wave function evolve as it moves through, is, for example, if you're thinking about wave functions in a band structure, you can write down what's called the Berry connection, which is just the gradient of the wave function, the expectation value of that gradient. But d by dk in momentum space is actually just the real space operator. So really what you're asking is where in the unit cell is this electron? So why is that relevant for nonlinear? Well, keep in mind that I might have some material with some band structure, but typically these bands come about from specific atoms in the unit cell, right? So the purple from the purple atom, the green from the green atom. So put a different way, when I shine light on the sample and I excite an electron from one band to the other, what happens in real space is physically this electron moves from being centered around one atom to being centered around another. So when I do that, what I've now done is to make a time-dependent dipole. And by Maxwell's equations, I know that a time-dependent dipole will give me a current. Okay, so this is what's called a shift current. It's a nonlinear effect that you can see in inversion-broken systems, for details I won't explain, that depends very strongly on the linear polarization of light. Right? So basically, if I send in light along X, I get a current along Y and in a certain direction. If I send it along Y, I get it in negative Y. Anyway, so what does this have to do with quantum materials? Well, if you had a material with a very large Berry connection, you would expect a very large shift current, and this might actually be useful for a detector of polarization. So it turns out that Dirac systems are perfect for this. And the way you can understand that is imagine that I was in a system where I had these 2 bands and I bring them to touch. Of course, at that point, I have no idea where my electron is. And it turns out you can show that in a Dirac system, you have this kind of monopole where this Berry connection is divergent. Okay, so what you expect is to have enormous nonlinear responses in these relativistic systems. And it turns out now, from work of my group and in fairness many others, we now know that that's not just PowerPoint physics, but it's really true. So we showed about 4 years ago now that in some of these wild semi-metals, you could get enormous shift currents that were the largest that had ever been seen in decades, coming about in the mid-infrared from these kind of nonlinear responses in this, from this quantum geometry. And again, you have an expert in the audience, but it turns out now people are trying to use these nonlinear processes as a way of probing this quantum geometry in materials. So if you're interested, I'd point you to a recent review that we wrote a couple of years ago. So I have to apologize, but I'm going to skip the axial Higgs. You'll just have to have me back, I guess. Sorry. Sorry, if I can get there. Okay, so in the interest of time and not putting everyone completely to sleep, let me thank the people who did the work. I want to especially thank Narendra Kumar, a former postdoc, actually now back in India as a professor, who helped start all the biosensing work, and my current grad student, Mike Gaiwitz, who's doing the ongoing work. I didn't talk about Yuping's work, so sorry, Yuping. But she's an excellent postdoc at Columbia. You should have her over for it. She did all the axial Higgs work and has really great stuff. Thanks to the people who paid for all the work, and also thanks to our collaborators in biology, especially Michelle Meyer, who we've been working with on the bioprobes for many years, and also Zhengmin Gao in chemistry we worked with, and the two companies that we've collaborated with on the biosensing. I didn't talk about this work, so I will skip it. So thanks to other people we've worked with over the years. And with that, I hope I've convinced you that these quantum materials are quite exciting because they have these highly interconnected properties that we can potentially make use of for sensing and really solving some of these issues about, trying to balance out the various needs in various sensing technologies. That graphene is really a fantastic material for biosensing, that it has, these wonderful structural properties that we can use for probing, and also this electronic structure, which really uniquely allows us to be very sensitive and specific, and that we've now developed a sensor that can do this multiplex sensing, and also that nonlinear optics could be quite useful both for sensing and for probing quantum mechanics. So with that, thank you very much for your attention.
Okay, thank you very much for your beautiful talk. Any questions? Yes.
I got a little bit lost with the application, but what is quantum in this quantum material? I mean, besides what is quantum in all your
Well, as you know, quantum equals cash, so. In all seriousness, no, it's a good question. So look, for us, it's maybe stretching things a little bit, I will admit that. But this linear dispersion turned out to be super crucial. So the problem that I didn't really go over in any detail about the semiconductors is, where this onset is of the signal depends on, it changes every time, right? So you can never really be sure how much charge is sitting there. In the graphene, the fact that you have this linear dispersion and you have this Dirac point gives you this kind of built-in marker of exactly how much charge is sitting on your device. So that really was crucial for us to get this reproducibility of, knowing exactly how much charge was on the device and therefore how much of the target. Whether you want to call that quantum, I leave up to you, except to say that, of course, for those relativistic electrons, we needed quantum mechanics. But sure, in every material, quantum is there. Yeah?
How do you calibrate the graphene transistors? Because I know that they're going to change device to device.
So actually, that's a great question. So the question is about calibration, right? How do I really know how much is there? And that's because each device is like a snowflake. So actually, that's one of the things we've worked very hard on in my group, is to try to get the devices to be as reproducible as possible. So I won't say that every device has the same initial Dirac point, but I would say roughly 80% of them do. And well, either they all fail or they mostly work. In any event, so the point is, what we found is that this initial Dirac point is very useful. So we actually measure not the shift in general, but the shift after we attach the aptamer. And what we're looking for are these relative shifts, right? So not the absolute number it gets to, but how much does it shift? And we found that that seems to be pretty reproducible, so long as this initial point is low enough, and also that the width of the Dirac peak is narrow enough, which means the mobility is high enough. In other words, it's clean enough. Yeah, but that's a huge problem. In fact, I would say until about maybe 2 years ago, we couldn't get good enough, reproducible enough CVD graphene, and that was a huge part of our problem. But thankfully, that has more or less been solved by the company. Yes?
Did you say you can use this to detect certain genetic sequences?
I didn't say that. That was actually what we originally had in mind. So we were thinking what you could do is put on some strand with some sequence.
Yeah.
There are other groups that have done that. Our experience was that we couldn't, basically you would need such a long strand, enough MERS, that to get it reproducible, that then your sensitivity would not be worth it. So we kind of gave up, I would say, on sequencing. What we do is the aptamers we use, the probes, those are a specifically engineered sequence, but they're really just there for, folding and unfolding in a selective way.
Clinical samples are loaded with proteins of all different kinds that stick to everything. How come they don't stick to your samples?
They're very special. It's a good question. So I think, there's two things. So first of all, I admit that we haven't worked with, oh no, that's actually not true. But anyway, in general, what we've been doing is this, we first filter and then we put it and dilute it in PBS. And I think that that allows us to operate at a level where this sticky problem isn't such an issue. In fairness, that's where we are, there's two answers to your question though. One is that we highly depend on the probe, right? So we really need probes that can really selectively grab the thing we want and not the thing we don't. And in fairness, what we do, which I didn't mention, is there's a washing step. So we expose the target, and then we wash, and then we measure. And I think that is crucial for the reason that you're getting at, that it might land, but the key is it doesn't stick. The other thing I didn't mention is we use a molecule whose name is of course escaping me because it's the end of the day, which is a very tiny molecule, but we use it to kind of fill the holes, right? So we try to make this forest as best we can of the probes, and we try to fill the holes with this other molecule.
Like PEG or something like that?
PEG, that's it, thank you, yes. So we put PEG in there to make sure it fills the holes. And the last thing is we've worked hard on this passivation, so that if stuff sticks in the non-active region, we don't care.
I have a quick question about this photo detector.
Sure.
Or this tantalum arsenide.
Yeah.
How efficient is your shift current? I mean, how much power you inject to your experiment?
See, he's an expert. So the honest answer is, if you compare us with other shift current measurements, we do really well. If you compare us with a real device, you'd rather use a polarizer.
Okay.
That's the honest answer. But part of that is because, of course, we were using a material that was highly reflective, and we didn't do anything to enhance the capturing of the light.
I see, I see.
So in fact, if we had, it was like 80% reflective. If you had accounted for that, if you could grab most of that light, you could boost the efficiency. But how competitive we would be with, say, a bolometer with a polarizer is a good question.
I see. That's a fair.
Yeah. So I personally don't think these are ever going to be good for highly sensitive detection. I think you're going to want them in cases where you want miniaturization and you want polarization sensitivity, but you're not as worried about absolute value.
Nice. Any other questions? If not, thank you again.
Thank you.